Hi, good morning, and welcome to this ZP webinar. So we like to do this webinar for the ZP Developer Zone every week, and today is the 17th of March 2024, and I'm literally going to just jump straight into it and just say that the questions that we're going to cover today are cyclic voltammetry. Somebody's got two potentiostats, a squidstat and a biologic. Neither of these potentiostats are sold or manufactured by ZP. ZP has its own range of potentiostats. But that said, I will take a look at the data today because we do it as part of our kind of goodwill towards the electrochemical community. I'll also talk about software for equivalent circuit fitting. Somebody's been watching some old videos. The software, I did try running it on a Windows 10, Windows 11 machine. I agree it doesn't run. But I'm going to show you the alternative now, which is Julie. And question number 3 is lateral flow strip integration. So somebody wants to, and I think it's a good one, integrate lateral flow with electrochemical sensing. So that said, let me go forward. Just to say a couple of things on the way here. Everything we do at ZP is really about making sensors, making electrochemical measurements, and getting that kind of data to the cloud. So, so we describe ourselves as a sort of sensor to API company. We primarily do it through contract development, contract manufacturing, though we have made some, I want to say, tools now or instruments that actually really speed up this commercialization process. So this is actually an electrochemical instrument. I've got one in the office, but it'll fit in the palm of my hand, just to kind of give you a sense of scale on that. We've got a webinar on the 26th of March. This will become relevant to anyone who's interested in actually commercializing electrochemistry or electrochemical assays. Please come to the webinar on the 26th of March. We do one in the morning, one in the afternoon, and we do these 2 sessions so that we can help people in different time zones. So if you're in Asia or Europe, the morning session will work for you. If you're in Europe, the afternoon or morning session will work for you. And for example, if you're in North, Central, South America, then the afternoon session will work for you there. And we also, if people are interested in electrochemical biosensors, electrochemical sensors, then we also do come on site and do workshops. And we also have workshops at our location. So every month, you'll find out that if you click the link, and if you see any links jumping up, I'll also put the links underneath the video as well. So we also do workshops at our site as well. With that said, let me jump into the questions again. So the first one was about somebody's running cyclic voltammetry both on a squidstat, potentiostat, and also a biologics potentiostat. As I say, I don't sell and I haven't manufactured either of these. But it doesn't mean we can't look at the data and try and figure out what's going on here. Again, they're actually using a ZP impedance spectrometer, and they need some software for equivalent circuit fitting, and I'll guide them towards that. And then lastly, that lateral flow strip integration between a lateral flow strip or lateral flow analysis and a electrochemical sensor. So we'll discuss that. So somebody's doing. They've got a series of questions. Question 1A is around about, they've got a difference between cyclic voltammetry on about 4.8 millimolar ferricyanide measured at 10 millivolts per second and 100 millivolts per second. They say there's a change. There's actually not that much of a change, and I'll go into that in a minute. Number 2, they're using 2 potentiostats, Biologics and Squidstats rather. Why do they look different? And I'll go into that. And question number 3 is actually it's a good question. I don't think your potentiostat is doing a conversion to SHE. If it is, it's a bit weird, but I think it's really just doing silver chloride. Pretty sure it's just doing silver chloride actually when I think about it a little bit more. Okay, but I'll dig into that as well. So question number 1A. This is data they got off the squidstats. As I say, full disclosure, I don't sell, I don't manufacture the squidstat. We do manufacture our own instruments, but it doesn't mean that I wouldn't support somebody if they reached out to us, which I'm doing now. They're using a working electrode, which is a carbon cloth, a platinum wire, and a they're using a silver chloride reference, and they're doing 100 millivolts per second. The first thing I notice when I look at this data, I think you'll show me here the first scan. So I think later on when I'm looking at the biologic system, I'm actually looking at the second scan. But it doesn't make an awful lot of difference for at least my broad analysis. So you're looking at the first scan and you're looking at ferricyanide. One thing I do notice is I'm not super familiar with the software on this Squidstat. Certainly not probably. I haven't seen one in about 5 years. I can see that your data points are quite stretched apart. I suspect what the Squidstat is doing is because you're doing 100 millivolts per second, its save rate is, is I don't want to say fairly slow, but I can see that if these points are actually true save rates, so then you've got 1, 2, 3, 4, 5, 6, 7, 8, of approximately 9, 10, 11, 12, 13, 14, 15, 16. Yeah, you've got 16 data points in there. So it's basically doing a very kind of, you don't have a lot of data over that entire experiment. So that's why it's so, it's interpolating. That's why it looks so jagged. So first of all, I don't know if the Squidstat allows you to alternate the save rate or change the save rate, but this wouldn't look quite this way it does if the save rate was a bit faster, let's say. But I think the way the Squidstat is doing it, it's giving you quite a low save rate. So I think you need to up the save rate slightly if the software will allow you. As I say, I'm not the manufacturer. I don't sell this instrument. But it looks like the save rate's a little bit low, so it's distorting your data. This will become significant in a bit as well. That the line along here, I mean, it's a screenshot that I've got, but I've really tried to struggle and get in there. And I think this says 5, and I really hope I'm getting this right, 5 milliamps. It says, I think it says 0.005 amps. So this will become significant in a bit. So anyway, so I've looked at the shape of your CV. It's distorted at 100 millivolts because the save rate is, I don't want to say too low, but it's quite low. And I've also made a point of that, noting what your current was later on. This is your 10 millivolt data. So it's the same instrument, probably the same electrochemical cell, the same materials and solutions in there, and carbon cloth, platinum wire, and it's at 10 millivolts per second. Now it's 5 milliamps again. So this time you can see that the save rate is much higher. So you don't get that kind of jaggedness because now actually you've got enough data points to actually give you this smooth curve. So strictly speaking, there's actually not much difference between your 100 millivolt data and your 10 millivolt data. It's just the save rate that's actually distorting this. That if you did the 100 millivolts at the same save rate, you would probably have something that looked like this, which is weird because actually they should look different, because this is 5 milliamps here. Strictly speaking, the square root of 10 is about 3, and the square root of 100 is 10. I'm doing that because your peak height should be proportional to the square root of the scan rate. So that means that when you're at 100 millivolts, you should be about 3 times the current at 10 millivolts. But you're not. You're actually at a really similar current. So that's kind of strange that you think that your CVs are different. I say actually they're only different because the save rate was too low on your 100 millivolt data, and if anything, the 100 millivolt data should be about 3 times the height of your 10 millivolt data. This is due to the Randall-Sevich equation, but it's not. It's actually really similar, in fact. So I think there's something sort of wrong with this. I've got a slight suspicion that your signal is potentially being limited by the platinum wire. That, in an electrochemical cell, in order to kind of have good analysis of that working electrode, the counter electrode should be fairly large. I've got a suspicion you've got a carbon cloth in there and platinum wire. But I do ask you to send me and I think that the ratio is not big enough between the the counter electrode and the working electrode. That platinum wire may be a bit thin, a bit for the area on that working electrode is my suspicion. There's a cut. There is. I'm going to put a link to this video as well, because I think that you should have more difference between your 10 millivolt and your 100 millivolt data than you actually have, because there's quite a large difference in charging currents between the two experiments, and you've also you've got a fundamental difference, which is current, peak height current in cyclic voltammetry should be proportional to the square root of the scan rate, and yours doesn't look to be that proportional to the square root of the scan rate. So there's a video here that I'd like you to watch. It's just for background information, but your big sort of statement is that why is my data different between 10 millivolts and 100 millivolts when on the Squidstat? It looks a little bit different by eye, but that's really because the save rates are different. But otherwise, they actually look quite similar, and they're not as different as I would otherwise expect. I'm going to have some statements at the end of here. Question B for you was, you then did a similar experiment on a Biologics. You gave me the Biologics data. I think this time you're showing me the second scan. So the first time around, I think I was looking at sort of, at least on the 100 millivolt, it looked like a first scan to me. I can see your conditions, 4.8 millimolar ferricyanide in 0.1 kCl at 100 millivolts, understood. I did wonder if actually what was happening here. I was looking at the reduction of ferricyanide to ferrocyanide here, and actually you just missed off the peak here of ferrocyanide to ferricyanide. I know you put ferricyanide in there, but when you start your CVs out here, for example, or if this is the second scan, you have generated the ferrocyanide essentially within the experiment. But I wonder if actually your CV would look more standard, in fact, if you went out of it further. Again, I think you've got a very large working electrode, and I understand why you have a large working electrode, because you're possibly in the sort of fuel cell space or biological fuel cells, or doing something more like an electrolysis type experiment rather than an analytical experiment, because again your currents are really high milliamps, which is fine. You know, I understand that's a reflection of your experimental space. It's not a criticism. I did try rotating and reflecting your data just to understand that maybe you were using some American conventions, which are a bit opposite to European conventions, but I was convinced, no, you seem to be running in the European conventions. Looks like the same electrochemical cell as you were using on the Squidstat, so understood. I'm only bringing this up because at ZP we do make a lot of screen printed electrodes. They're really good. Because of this person's currents, I think they're much more in the kind of synthesis, electrolysis, fuel cell, battery space with the more power applications, whereas ZP is more in the sort of analytical space. But I bring it up because we do make a lot of screen printed electrodes, and we do characterize them with ferricyanide. So we probably make thousands of experiments a month, actually, just similar to what this person's doing. I only bring it up because I think it might be a good idea for you to actually get a screen printed electrode, put ferricyanide on it, and just test those two instruments and compare them to our data. So I'll bring up our data now as well. So this is not just one screen printed electrode, this is several screen printed electrodes. So it shows that we get really good reproducibility. We get a kind of classic cyclic voltammetry for ferricyanide. And as I say, that all comes from this hypervalue carbon electrode. So I was thinking a little bit, if you're unsure about your instruments, then actually take a screen printed electrode that's well characterized like ours, because we have thousands of data points per month being generated on it, and actually just see what the data looks like on those two potentiostats. It'll probably help you to set those potentiostats up a little bit more. I'm a bit worried about the save rate on that Squidstat. Nothing wrong with Squidstat. I'm sure it's a great instrument. It's just the save rate. I'm sure it's something you can actually control. So your Biologics instrument was actually starting to look a bit like our CV, just out of interest, because we're using the reference electrode that's on the screen printed electrode, and you're probably using a more classic glass silver chloride electrode with silver wire in that glass electrode, probably with some potassium crystals in there. So we're at slightly different potentials, but I have looked at potential versus chloride concentration, and so we're measuring versus about 0.1 millimolar chloride, whereas you're probably measuring versus more like saturated potassium chloride. So I've understood that, you know, we have a reduction potential for ferricyanide to ferrocyanide a reduction potential, a reduction peak of close to 0. It's about here, and you've got a potential that's actually out here. But the difference between our two peak reduction potentials, or is the difference in our chloride concentrations between our two reference electrodes. So I have accounted for kind of that, and it still makes sense to me. So I think you were going to get a good CV on this Biologics instrument, but you just missed off the oxidation peak. No big disaster, to be honest with you. If I was really going to test that instrument, I would actually be getting that hyper value electrode and actually running those solutions on that, and making sure, and then comparing it against this video, and that would tell you whether your instruments were working right or set up correctly. So I've looked at our ferricyanide experiments, your ferricyanide experiments, and your ferricyanide experiments, both on the Biologic and the Squidstat. Please send me a photo of the experimental setup, as I suspect that you may have a connection problem rather than an instrument problem. So sometimes what I'm seeing your data sometimes is what I would call IR distorted. And it's no criticism of you, and it's no criticism of either of those instrument manufacturers. It's just send me a photo of your experimental setup. It may help me to essentially help you. I've got a super suspicion that your working electrode is quite large. I've just done a back of the envelope calculation, and I wonder, I mean, I know if I get it wrong, I'm sorry, but it seems like you might be kind of like almost 40 centimeters by 20 centimeters. I've done this because maybe it's just your signal is very distorted with charging current, but you do seem to have quite a large working electrode. I've obviously looked at our current. We're approximately 5 millimolar as well. So we're 5 millimolar ferricyanide. You're 4.8 millimolar ferricyanide, so pretty close. Our working electrode is 4 millimeters squared. So using those two numbers, I can see that I can see that I've when I look at this, when I look at the Biologics data, in fact, I would suggest then that that's not so much 40 by 20, but it's more like 20 by 10. But what I'm saying is I can see that your orders of magnitude larger than us. So I'd be quite interested in seeing a photo of it. I'm quite interested in knowing the working electrode area as well. So my kind of advice is I think you need to test on a model system to test those two potentiostats. I've put a connector here. So one thing is, I know your business is all, well, not your business, but your research is all about much larger experiments or larger scale experiments than us. But it's a good idea to actually have tested those instruments on something that's fairly well characterized. So I take this hypervalued carbon electrode, take some of these connectors, and we have some connectors here. If your potentiostat has 4 millimeter banana plugs, you need these. If your potentiostat has 2 millimeter banana plugs, you need these. I suspect that at least that Biologics instrument is 4 millimeters. I don't know about the Squidstat. So I have looked at your data, compared it to our data. I think that your data is what we call IR distorted. So if I took my data and I distorted it by IR, all I've done is stretch the image out. It stretches. A lot of your data looks like it's IR, and it's no criticism of you. I think it's because the electrode is large, you're passing large currents, and I wonder on the Squidstat, when you did the Squidstat, whether there was a high impedance connection being made. But send me a photo, it might help me. So I think you've got an IR drop. I wouldn't call it a problem, but I think it is distorting your data. I think the electrochemical cell is not completely set up the same between the two experiments. And just the simple fact that those crocodile clips, or how you're making that connection, might be different between the two experiments. Send me a picture of the electrochemical cell. I think that's what's distorting your data. Question number 2. This is nice. Somebody actually has an Anapot EIS. They have a potentiostat from ZP. They were trying to use some free software that we give. We used to distribute, but it hasn't been updated in years. I've also got a Windows 10 and Windows 11 like machine, and I tried it. So we've gone over at ZP to Julie, and so I did try that software. I agree it doesn't work. We've all gone over to Julie. I haven't used this software in years, but I have a couple of videos here that I want you to watch, and I'll also link to those videos below. Julie is an online cloud data system where you can actually upload EIS data You can fit EIS data using equivalent circuits. It'll tell you how good the fit is. And you'll also watch those videos. You'll also go out there and search the literature and look for papers that, if you make an equivalent circuit, it will actually find you papers that are also using a similar equivalent circuit. It can be quite useful. So those two videos are linked to here. I'll put these links underneath this video when I've finished. And here's Julie. Here's how you can get it. Get yourself an account. Start playing with it. And once you start playing with it, give me some feedback. Question number 3 is about lateral flow analysis. We do get, over the years, people have asked me, can you integrate between an electrochemical sensor and a lateral flow strip? And I've always said that you can. I will dig into that a little bit more now. Do we need to activate? They've got some hypervalue carbon electrodes, which I didn't think about the connection, but hypervalue carbon electrodes were what I was linking to earlier on in this video. They don't need to activate them by running them in something like buffer. We don't do that. We just use them as they are. It's a good question, because if it was gold electrode, I honestly would be getting you to activate them, because gold tarnishes. But carbon in some ways is, I think, is more, gold has a reputation for inertness, but gold actually tarnishes. It picks up stuff from the atmosphere quite a lot. But at ZP, we never is a strong word, but I don't think you need to clean those carbon electrodes before you use them. I do hear what you're saying, that the lateral flow strip is 5 millimeters, which is a good point, because if there's an industry standard and it's 5 millimeters, it's not a good idea to necessarily break that standard. So if it's 5 millimeters, then I think you can get away with just using 5 millimeter width on the electrode as well. And the blue material that you're referring to is an insulator, and yes, you could put double-sided tape on that insulator and everything would be fine. I will illustrate the answers here. So here's the hypervalue electrode. It's about 7.2 millimeters. I always just lazily call it 7 millimeters. You can put adhesive tape on these areas. So there's a bit of whiteness up here. You can also cover that with tape as well. So you can cover that with tape. You can put the lateral flow material across like that. It doesn't matter. Your instincts are correct that you've actually left this bare. It won't affect anything. Obviously working electrode here, reference electrode here, counter electrode here, and put the sample on there. Of course, you'll only really get a signal once the material is wicked down and across that strip. It might be worth setting this up and actually just trying out a ferricyanide experiment on this, 5 millimolar ferricyanide, which is a good point actually, because if you watched question number 1 today, I show you that we have a lot of data on these lateral flow strips in 5 millimolar ferricyanide. It's not lateral flow strips, electrodes rather. So they're just baseline you. What does a cyclic voltammogram look like, going from an electrode where I just pipetted on ferricyanide to an electrode where I brought the ferricyanide to that electrode using the wicking of a lateral flow strip. That might be just a nice first experiment to characterize what that looks like. This person already knows, they've already attended our webinar, but this, if they work on this kind of format, it would click quite nicely into our Sense It All platform later on as well. So they actually have quite a nice pathway to commercialization as well. If you're unsure about this, and again, the same person, come to the next webinar, because we're always updating and there'll always be sort of new interesting things for you to sort of find out those webinars, and that'll be on the 26th and 27th of March. And don't forget, we do one at the end of every month anyway, so just, even if you're coming to this video later, just see the link and it'll probably show you where the next webinar is. So question number 1, cyclic voltammetry on Squidstat and Biologic Potentiostat. In fact, your CVs on the Squidstat at 10 millivolts and 100 millivolts were not so different to one another. I would have expected them to be, the currents to be about 3 times more on the 100 millivolt experiment as opposed to 10 millivolts, but that really wasn't the case. The difference was actually the save rate was very different between those two experiments. The Biologics Potentiostat, I think, was going to show you a more classical... sorry, I've got something 3D printing in the background, so... The Biologics Potentiostat was going to show you a more classical CV, but I think you just missed the peak. On both instruments, I think you are IR distorted. Again, it's no criticism of you or the instruments. It's actually you're doing quite large electrode area, and that would be to be expected. I think if you run a troubleshoot that instrument, those instruments, or understand those instruments more, do the kind of, get a hyper value carbon electrode from us, get the connectors, and just do, so then you've got a way of always, you know what you're expecting, you see what the instrument gives you, and then that would help you understand those instruments and the settings a little bit more. I've also asked you to send me a photo of the setup as well, because I might be able to give you an insight by looking at the setup, not the instrument, sorry, the electrochemical cell. Software equivalent circuit fitting, yes, I did check that software myself. I've got a similar spec PC to you. Go over to the Julie software, the Julie system. It is cloud-based as well, so it doesn't matter what instrument you're on, as long as you've got a browser and internet connection. And lastly, lateral flow strip integration. Lateral flow strip integration. I would stick with a 5mm width, because then you're staying close to the way people actually manufacture lateral flow strips. I didn't suggest it in the video, I'm not going to suggest it now, but see, because in the end, if you want to go with 5mm, it's not that hard to actually make a 5mm wide electrode. But don't go to customization too early. Too many people go to customization far too early. If your customization just leads to poor reproducibility of manufacturing, so stay where you are. But your instincts were correct. You can stick sticky tape to the blue insulator, and you can have that 5mm width strip on that 7mm electrode. It should work fine. So if you've got any questions with ZP, you can see we put quite a lot of work into answering these questions. Don't hesitate to reach out to us. Okay, thanks very much.